Our new method called UnSAMFlow explores using segment anything model to improve unsupervised optical flow estimation. Optical flow reflects pixel-level motion between two consecutive frames. For each pixel in the first frame, its optical flow is defined as the 2D vector pointing to its correspondence in the second frame. Many recent works focused on the unsupervised estimation of optical flow due to the lack of ground truth labels. These methods are usually trained with unsupervised losses based on the assumptions of appearance constancy and flow smoothness. However, these assumptions do not hold at occlusion regions where the background pixels are no longer visible, and around motion boundaries where the motion is not smooth. Fundamentally, these issues both stem from the low-level nature of optical flow, where object-level information is generally missing. Therefore, in this paper, we explore using object-level information to guide unsupervised optical flow. Previous methods use semantic segmentations to provide object-level information. However, these segmentations do not separate different instances and may not work for novel objects. In contrast, we propose to use SAM, a recent general-purpose large foundation model, to perform object-level segmentation. We considered two different problem settings depending on whether SAM is needed during inference. In setting 1, we only use SAM during training to help better train the network. In setting 2, we add SAM masks as additional inputs to the network, so SAM is needed both at training and inference time. Comparably, setting 2 should yield better results, but at an extra cost of inference time due to SAM computation. Our network is based on AR flow. We propose 3 adaptations. First, semantic augmentation adapted from SAM AR flow. We first use SAM masks to find key objects in the datasets, and then copy and paste these objects across samples to generate new augmented samples during training. This adaptation adds strong self-supervision to better handle occlusions. Second, we propose a homography smoothness loss to replace the previous edge-aware smoothness loss. Previous methods generally use edge-aware smoothness losses where they do not penalize across the estimated edges. This causes issues because the gradients are concentrated only around the edges of the estimated flow, even if a region of flow is inaccurate. The landscape of the loss function is also visualized on the right. The function is rather flat around the current estimate, so it is hard to optimize. Therefore, we define regional smoothness by homography. Given an estimated flow, we first find SAM objects that potentially contain large occlusions, and then estimate the homography for each selected object. We apply refinement and use the refined flow to self-supervise. Our homography smoothness loss directly penalizes the entire region instead of only around edges. We also consider adding SAM masks as additional inputs to the network to better enhance the results. We propose a simple mask feature module in the decoder to aggregate features on the object level. More details are discussed in the paper. We tested our methods on both Singtel and KD datasets. We can see that all 3 adaptations help improve the results, and our final model outperforms previous unsupervised methods by a clear margin. This suggests that object-level information from SAM can guide unsupervised optical flow significantly. Qualitative examples also show that our method produces clear and sharp optical flow outputs that are consistent with the segmentation of objects. Ablation studies justify the effectiveness of our each proposed adaptation. Experiments also show that our method can better generalize across domains. For more details, please refer to our paper and code. Thank you.